All right, now we're going to do every single set building operation. Earlier, I should have had a video going over how to take subsets of sets, unions, things like this. Now we're going to go over all the operations you find in mathematics, where you start with smaller sets and you build new sets or bigger sets. And the key operations we're going to go over are Cartesian product, taking modulo and equivalence relation, power set, and function set and Hom set. And there are a lot of ways to do this because these things come up a lot throughout all of mathematics, but I thought I would go with the ever popular, how do you make every single number? So starting with the natural numbers, the numbers like 0, 1, 2, 3, how do you make then negative numbers, and then rationals, and then reals, and then complex numbers? And so I'm just going to go through each of these operations and use as key examples making all numbers and hopefully understand the numbers a little better. And so along the way, to understand things, you need other examples too. I'll talk about similar triangles for equivalence relationships. I'm gonna do the construction of going from rationals to real numbers twice, and I'm gonna do two different constructions: Dedekind cuts and Cauchy completions. And the reason I'm doing that is, of all of these steps, the NZQRC, going from the rationals to reals is the most subtle, and it's the least well understood. And so I'm going to spend more time on that. I'm going to give two examples. You notice most of the time when you use real numbers, unless you've seen a construction of the reals, you've probably never seen a definition of the real numbers. And so I'll go over all that. And with these two constructions, hopefully, you come out of it understanding, having a real feeling of what a real number really is. Because that's the hardest step, going from rationals to reals, not reals to complex numbers. Along the way, I'll give a proof that 0.9999 repeating equals 1. We'll talk about how infinite decimals work. Then I'll talk about philosophy of number constructions, because sometimes I feel like even after you've gone through all of these constructions, people get a little bit of the wrong idea of what these constructions are or are for. And then maybe I'll talk about some other stuff along the way. But start off, we're going from natural numbers to the integers. So what are the natural numbers? Now, it's already a little bit controversial because some people say natural numbers start with 1, 2, 3, and some people say it starts with 0, and they say the whole numbers are 0, 1, 2, 3, etc., etc. This often actually changes depending where you are. I think more often in like France, you'll start with 0. If you go to France, their elevators, the ground floor is 0, and they'll have negative numbers and things like this. But to keep it simple, we're going to start with 0, and I'm not going to construct the natural numbers. There's lots of constructions of natural numbers starting with boxes for boxes, but I actually think starting with kind of your atoms as natural numbers, 0, 1, 2, 3, these are very intuitive. We have an idea of having 3 things or 2 things or 1 thing, and maybe I'll have a whole other video on constructions of the natural numbers because I have different opinions on that. But one of my biggest opinions is that I think the most natural starting place is with the natural numbers rather than, say, these boxes of boxes that go down to the empty set. But to construct the natural numbers, we're already going to need 2 key tools: a Cartesian product and taking something modulo an equivalence relation. So, Cartesian products. Right, Cartesian products. So what is a Cartesian product? We write it with this little times. That sort of looks, maybe you could say, Descartes-esque. And essentially, what you do is if I have 2 sets, A and B, all I do is I make these ordered pairs A comma B with A and B and B. And so what does that mean? Well, we'll start with this first example. We'll start with, let's say, the product of these 2 sets, which we'll call A and B, and see what we get. Well, the pairs we'll get will represent it, let's say, lil and big. Maybe not the best handwriting. And then we have A, E, and problem. And the pairs you'll get lil comma A, big comma A. I'm going to move this down. There's already not enough room here. Am I moving too many things? I'll move some of it back. Yeah, we'll move some of this back. You get back over there. Then let's make some more room. put the E here, and let's put problem all the way here. Problem. Right. And then we have pairs lil comma E, big E. Maybe some of you guys know big E. Lil problem. And big problem. So I kind of chose these sets a little arbitrarily, but you can already see that I start with a set of size 2 and I have a set of size 3, and when I take their product, I get this set of size 6. And so this is kind of how we take a product of sets. It allows us to have data that's, you could say, tabular, where you have multiple values. And more or less, the way to think about it is if we think about it on two axes, if we have an axis A and an axis B, and you can think of all of these points on A and B as being elements of A and B, the points of the Cartesian product are exactly this product square of all those pairs. So imagine, going back, if this is E and this is lil, you can see graphically lil comma E would be this. And the easiest way to see this, and the second example of Cartesian product, Cartesian product is not the most complicated of things, is we can take the Cartesian product of the real numbers with the real numbers, which we haven't even defined the real numbers yet, but then we get something, r times r equals r2, that we call the Cartesian plane. And this is really where the Cartesian product gets its name. That, if we have coordinates like, let's say this is 3, and this is, -4 or something, we would have, here would be 3 comma -4, and we have a product of two sets. And this gives us Cartesian products. There's not as much to say about Cartesian products off rip, but as more examples come up with them, I could talk about more properties. But the second tool we'll need, which will be a little more involved, is taking mod and equivalence relation. Now, I feel like this is something which perhaps, I think many more people have heard of the Cartesian product or seen products of set than maybe have even ever heard the words modding by an equivalence relation. And part of that is that this is something that you really only start to hear a lot about maybe if you're taking an algebra course, an abstract algebra course. And it's something that kind of exists in the background a lot of the time, and it has a lot of parts. It's a little intricate. I have to define what an equivalence relation is, and then I have to define that once I have an equivalence relation, what does modding by an equivalence relation really mean? And so an equivalence relation that I have written out here, because it's more important, I wrote it earlier so that you don't have to deal with my bad handwriting, is really, you could think of a generalization of the idea of equality. That we want to say two things are similar, and this tilde, whatever this relation is, it will tell us when two elements of a set S are similar. And we want it to have some properties that make sense for similarity. So one, the first property is that everything should be similar to themselves, which makes sense. The second property is that if A is similar to B, then B is similar to A. That makes sense. And then if A is similar to B and B is similar to C, then A is similar to C. And so the first example, and almost the tautological equivalence relation, is that equality equals is a form of an equivalence relationship. If I have any object, I know A equals A always holds. If A equals B, then B equals A. And similarly, if A equals B and B equals C, then A equals C. Very similar, or very simple. Now, the next type of equivalence relation I'm going to talk about illustrates the difference, say, between equality and different equivalence relationships. And I'm going to talk about first, even though I said isometric and similar triangles, I'll start with similar triangles. So let's define a space of triangles, and we'll say the space of triangles are really just like these subsets of the plane made by three vertices. So we'll give the classic right triangle the 3, 4, 5 triangle. And so here's one triangle. And let's make another one. Why not? Everybody loves the 3, 4 triangles. A perfect 3, 4 triangle. And so the first thing I would want to express is that these two triangles, even though, they might seem identical, they're not equal. As subsets of the plane, and we're just considering these edges, and imagine I drew them better such that, it actually snapped to the grid. These guys are not equal, but they are similar. And what I mean by similar is that I can make a transformation of the plane. In fact, I can just translate. You can move this triangle into the other such that these triangles would be identical. Another example of a similar triangle is I could say have one facing the other way. And I could have this mirror image. Now this guy, I can't just translate into either of these, but I could reflect it. I can give a transformation of the plane that would make it so that this triangle gets mapped into this triangle. And the last one for similarity is that I can give 1, 2, 3. I'll do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're doing a 6, 8, 10 triangle. And this one I would have to translate over to show that similar, but I'd also have to scale it down. And so we say like two triangles, T1 is similar to T2 if there is a transformation of the plane, which I'm being slightly vague about, but it means I can do scaling, I can do rotation, and I can do reflections and compositions of those to go from T1 to T2. If I can do a bunch of transformations of the plane to show that one triangle can be mapped to the other, they're similar. And so then the thing to check is this relationship an equivalence relation? Well, first thing to check is that a triangle is similar to itself. And the transformation that you do of the plane, the way you map our points, is you just do nothing. It's called the identity transformation. Then, if T1 is similar to T2, does that imply... Oh, did I just turn this off? Does that imply that T2 is similar to T1? And there the answer again is this also holds. And the reason is that if I do any of these transformations like scaling, reflecting, or rotating in one direction, I can just do those transformations sort of like rolling the tape in reverse to go in the other direction to get from T2 back to T1. So if I scale down by 1/2, I can scale up by 2. If I translate over to the side, I can translate back. And so basically to show that if T1 is similar to T2 by a bunch of transformations, to go back from T2 to T1, I just roll all those transformations in reverse. And then the last one, which I'll move down a little bit for to show, is that if T1 is similar to T2 and T2 is similar to T3, then that means that T1 is similar to T3. And here, we essentially, if the previous one was proven by rolling a tape one way and then rolling it backwards, this one we know there's some composition of transformations that gets us from T1 to T2. And we know there's some transformations that gets us from T2 to T3. And so to show that T1 triangle is similar to T3, we just go through both of those sets of transformations to get all the way from T1 to T3. And so this gives us the intuitive notion that similarity of triangles is also an example of an equivalence relation. But it's not the only equivalence relation that you might consider for triangles. For example, I also wrote something that is isometric. And so isometric is something that's a little bit stricter than similar triangles. So we say two triangles are isometric if I can get from one triangle to the other by these movements of points, but I'm not allowed to change distances. I'm not allowed to do scaling. Like, for example, the way I showed that these two are similar under, the definition of similar triangles is I had to do a scaling by 1/2. But when I'm doing isometries, these two would still be similar, and these two triangles would be similar. If I'm only allowed to do transformations where the distances between points don't change. But all three of these triangles would no longer be similar to this. And the reason I just want to bring that up is that very often on sets you have different notions of similarity, and some of them can be more restrictive than others. And the last thing I want to do is define, okay, once we've done all of this, what does this get us? Okay, we have a notion of things being similar. How does this relate to building sets, and how is this going to come back all the way to allowing us to go from the natural numbers to the integers? Well, now that we have a notion of similarity, we can do something called modding by an equivalence relation. And this is the real bread and butter that we use all this kind of operation crowds algebra. All the algebraic constructions involve, if not explicitly, they often involve, there's some modding by an equivalence relation happening. And what this does is that, essentially, what I would say is that, say I have a set of things, like I'm talking about triangles, like maybe I have isosceles triangles here, and I have this, right triangles, etc., the space of triangles. And I have some of them are similar, like maybe I have a really small equilateral triangle, and this is similar to that. Well, when I mod by an equivalence relation, I consider all of these equivalence classes. And so an equivalence class is that, say, now I'm talking about imagine this is a well-drawn equilateral triangle. It's definitely not. It's a little crusty, I would say. But the equivalence class of this, which we would often write by putting these two brackets, is a subset of the set of all triangles S of the plane of all of the other triangles which are similar to it. So you could have the reflected image of it. You could have a smaller one. They're all like little Dorito pieces. You could have one rotated over here. And so this is what we call the equivalence class of a triangle. And when we mod by an equivalence relation, we're taking a set S. So here's our set S of all of our triangles. And we're kind of compressing it by saying, you know what? Not only do we have all of these different elements are similar to each other, we're going to almost treat them as they are equal to each other. And so that's what this relation here is saying, that if A is similar to B under this equivalence relation, then the equivalence class of A is equal to the equivalence class of B. And so, example here is that the equivalence class of, an upside down little triangle, if it's still equilateral, is equal to the equivalence class of our, oh wait, I should, imagine that line's not there. I'll erase it. Is equal to the equivalence class of our bigger, right side up equilateral triangle. And then what this allows us to do is that once we take our set S and we compress it into the set S mod tilde, so our triangles modulo singularity, is it allows us to study all of the different types of triangles up to similarity. So for example, we notice, there's only one equivalence class where all the sides of a triangle are equal. And so that's the equivalence class of all equilateral triangles. So there's just one element in S mod tilde of all of our equivalence classes that represents an equilateral triangle. Then we can see that, okay, well now there's a bunch of, let's take our isosceles triangles. Isosceles are triangles where two of them have the same length. And let's say the third one, and isosceles and not, what are the different equivalence classes for isosceles triangles? This, takes a little math and proving, but you can show that, say the one edge of the isosceles triangle that's not of equal length to the other two, we can always scale any isosceles triangle we have such that that one edge that doesn't have the same length as the other two, which I'm using the letter S for, which is bad practice. I feel like math lecturers do this all the time, reusing letters by accident. We can see there's a bunch of different classes of isosceles triangles, basically, that we can index by having different lengths S. And so basically for, every S greater than 1/2, if it's close to 1/2, we would have a edge 1 and the isosceles triangle would be really, really shallow. But for all S greater than 1/2, we have an equivalence class of similar triangles, of isosceles triangles that look like this. And then we have a bunch of equivalence classes of isosceles triangles, which are right triangles. We have the 3, 4, 5 equivalence class. And so now using this operation of taking modulo equivalence class, it allows us to say when things are similar, we can treat them as equal once we compress it by taking mod in equivalence class. And this happens all the time, and you can actually spaces of similar triangles relate depending on how you define similarity to even spaces of elliptic curves, which are involved in all this other mathematics. And so this does relate to more deep stuff. But in practice, when we're building new sets, this is actually not often what we do. And so that's why, even though this is an intuitive way to think of equivalence relations, I want to give one more example, which is sets of size 2 from products. Because more often, the reason we use modulo and equivalence relation is that we're trying to build a new set, and what we do is we add a lot of stuff. It's like, imagine you're making a clay sculpture, and so you add a bunch of clay pieces, and it's like all big and flabby, but then you need to scrape away because you've added too much, and it doesn't look like what you want it. Maybe you're trying to make some dragon or whatever. And so very often we do a bunch of operations to add all that clay, and we use the modulo equivalence relation to scrape away and refine and get the set that we're looking for. And so I'm going to construct, starting from a set S, in kind of a roundabout way. It'll make more sense once I get back to the numbers. Say I have a set S, I'm going to go to, instead, the set of a set T, which is subsets of S of size less than or equal to 2. And here's what I'm going to do, is that I'm going to start with S, and I'm going to be like, well, how do I get more elements? Or how do I get two things? Well, I just learned about taking products, so I can do S times S. And if I do S times S, this will give me all of these pairs, S1 comma S2, such that, S1 is an S and S2 is an S. But, S1 comma S2, this sort of looks like sets of subsets of size at most 2. But in this set, in S times S, S1 comma S2, if these two elements are not equal, S1 and S2, will not be equal to this. And that's not how subsets work. In subsets, if I have two elements and flip them, then they should be equal. And so that's what I'm going to do. I'm just going to define an equivalence relation on, equivalence relation that says, A comma B is similar to C comma D if these are two elements of S times S. And I'm going to say these two things are equivalent if and only if, write this symbol, either A equals C and B equals D, or the reverse of that, and A equals D and B equals C, which more or less says that A comma B equals C comma D, or if I swap B and A, that B comma A equals C comma D. So all I'm saying is that when we have this kind of situation where they're not equal, I'm going to use this equivalence relation to just say that they're equal. And you can check that this has all of the properties of being an equivalence relation. And so when I do this, I take the set, S times S, and I take it modulo an equivalence relation tilde, and what do I get? well, I get a bunch of these equivalence classes of these things, of these a comma b's. And when I look at those, I'll notice that, like, for every a in S, I'll get the equivalence classes of like a comma a, and those classes will only contain just single elements, and so I'll have all of the subsets of S of size 1. And then if I have two elements of S, comma b and S, the subset a comma b will be represented by the equivalence class of a comma b ordered. But this equivalence class, by our definition of the equivalence relations, is equal to the equivalence class of b comma a. And so this way, this application of like adding clay and then scraping off is a little artificial because there are other ways to get all the subsets of size 2 or 1. But it shows you how in practice these constructions involving modular and equivalence relation come up. An example that's actually very similar to this is the example I'm talking about in this video, and I'll happen multiple times, which is constructing new numbers. So going back to this, we're now going to look at our two tools, the Cartesian product and modular and equivalence relation, and we're going to use this to go from the natural numbers 0, 1, 2, 3 and to the full integers. And we're assuming we also have, we have a notion of like 1 is less than 3. There's all these structures in the natural numbers. It's not just a collection of things. We can add stuff, we can multiply stuff. We want to be able to do all of that with the integers too. And so how do we do it? Well, we do exactly that thing in 3 steps. I wrote 2 of the steps. Maybe I should have broken this up. But the first step we do is that we add, we take the product of the natural numbers with itself, and then so that's adding a bunch of clay, and then we scrape out by this relationship a comma b tilde c d if a plus d equals b plus c, and then for n in the natural numbers, n goes to n comma 0. Now, if you're just looking at this, I did write more over here. I'm going to move this guy all the way over here. If you're looking at this, and you're me, you're thinking, what the hell is going on? Like, what are we doing? Well, I'm just going to tell you what the idea is here because it'll make everything much easier in sort of working backwards. Like, if I want to have negative numbers only using positive numbers, how would I do this? And one idea is that, well, if I have, what is negative 4? In essence, negative 4 is what you get that if I were to add this to 4, I should get 0. And so really I need a way, well, one way to do it, that if I only have, starting out with these positive natural numbers, I could just say, well, our numbers are exactly these pairs a comma b, where a comma b sort of equals, in quotes, a minus b. And this is a common way that if you have to construct something and you're moving backwards, that like, okay, I only have positive numbers at my disposal. What I'm going to do to construct them is I'm just going to say, well, I need some information to get negative numbers. I'm going to put in a second coordinate, adding clay. And I'm going to say that second coordinate just says that, if my number is adding by a, then it's adding by a and then subtracting by b. And you say, okay, well, that's interesting. That already gets us some stuff. For example, we get our negative numbers. Our negative 4 would just be 0, 4. But the problem is we've added too much clay. We have a lot more elements here. We also have negative 4 would be represented by 1, 5 and 2, 6 and a lot of other things. And so we need to go from these pairs a comma b and we need to collapse it down, removing that clay. And how do we remove that clay? With this equivalence relation. So basically, what this equivalence relation, how do we get this, it's equation a plus d equals b plus c? Well, you just work backwards again. You say, well, if a comma b is really in behind the hood is something like a minus b, and if c comma d behind the hood is something like c minus d, then all I need to do to show that these two things are equivalent and equal is solve this equation. A minus b equals c minus d, which with the mathematics that I have at my disposal, I can add positive numbers. I know that this is the same equation if I add on both sides as a plus c equals b plus d. And so this is exactly the relation that we have, is we say that 0, 4, which represents negative 4, is equal to 1, 5. Why is that? Well, because 5 plus 0 equals 1 plus 4. Basically, because the a minus b equals the c minus d. And this allows us, starting just from our natural numbers, which only have 0, 1, 2, 3, to construct these negative numbers in a meaningful way. And so we have all of our negative numbers there. We also have our positive numbers. The version of positive 4 is 4, 0. Now we want to do some other stuff. We want to be able to add, and we want to be able to multiply. Well, adding is actually very easy. Let's see what's on addition, multiplication, and ordering. Okay, yeah, let's just go through all of these. Let's do addition. How do we add these? You can pause if you want to say how one adds a comma b plus c comma d. Well, it's very simple. You just say that this is equal to a plus c comma b plus d. And again, the intuition behind that is you should be thinking in your head, what is this? All right, addition squared away. We can already see that if I have 4, 0, which is, this is positive 4, and then we add that to 0, 4, which this is negative 4. To make this not confusing, I'm going to remove this equals. What does this equal to? Well, this is equal to 4, 4. And 4, 4 is also equal to 0, 0. And so we see that our negative numbers are acting exactly how we want it to. 4, 0 plus 0, 4, which represents negative 4, is equal to 0, 0, which is 0. Now, how do we do multiplication? Multiplication should be the most complicated one. But again, it's still doable. So you can pause again if you want to work this out for yourself. But I'm literally just going to write this and collect the terms. So what is this equal to? This will be equal to AC, because I have positive A times C, plus BD, comma, BC plus AD. And that's how you do multiplication. And you can check this. You can check this here. I'm going to do 2 times 2, but I'm going to do it with two weird representations. We're going to do 2, 0, the simple one, and then we're going to do 4, 2. And let's see what we get by running this formula. All right. A times C plus B times D, that will give us 8, because we get the 2 times the 4, A times C plus B times D. Then B, well, B is equal to 0 times C is 0. And then A times D, which is 2 times 2, which is 4. And then we can simplify this by subtracting 4 on each side to see that this is equal to 4, 0. And so we've shown, using algebra in a weird way, because these two elements, once we mod out by the equivalence relation, are both just equal to 2, 0, as equivalence classes. I'm being a little loose with notation, and this happens a lot with modulo equivalence relations, because really, instead of writing these two pairs, around all these pairs, I should put these like square brackets. Because I'm not multiplying the pairs, I'm not multiplying elements of n times n. I'm multiplying elements of n times n modulo the equivalence relation. So they're all really sets of pairs. You know, the element 2 is really the set that is like 2, 0 and 3, 1 and 4, 2 and so on and so on. But in practice, and basically just for convenience, this happens all throughout, you know, if you do a lot of math, your mathematical life, people just don't write down the square brackets. we just like omit them. And based on context, you're supposed to know whether we're talking about, you know, the literal pairs or we're talking about the equivalence relations. So I'll continue to do that, but you should know that in the background, that's the objects we're talking about. Now, the last structure is when is, you know, an element a comma b less than or equal to c comma d. Ordering. Well, you go back to our when is a minus b less than or equal to c minus d? Well, it's exactly when a plus d is less than or equal to b plus c. And with this, zooming out a little bit, or zooming out a lot, and going back, we have constructed, just starting off from natural numbers, 0, 1, 2, 3, etc., and we built all of the structures that we need to have negative numbers and to have it so that everything has an additive inverse. That if there's 5, you know, an element 5, which we represent as the class of 5 comma 0, there's an additive inverse, which is just 0 comma 5. And so this would be equal to 5, and to be careful, I'll put these things around it. And negative 5 is equal to this class. And that gives us all of the guys that we want. And this can be a lot. Let me know if this stuff is confusing, because I've gone a little quickly. Because this is something that I feel like happens a lot in mathematics, where there is something that technically the logic is not that complicated. The argument is not that complicated. None of these arguments are that complicated. All of these arguments that I'm doing are really just doing algebra of addition and subtraction with these pairs a minus b. Like, that's it. But oftentimes it's difficult to understand because it's just so foreign. Like, a lot of the difficulty in mathematics is that it's a bit of a foreign language. And so just working and getting that fluency with stuff like taking products or taking stuff mod and equivalence relation, it can just be so unintuitive at first that it just takes time to sit with and to become comfortable and fluent with it. That's why all the time in mathematics, there are very often times, all the time, there are concepts that when you start to learn it feel impossible, just so hard. But once you get it, they're extremely easy. And I think this is a thing that if you feel like you don't get this construction, I would literally just write it out, do it again, because this is the type of thing that before you know it, it feels impossible, but once you get it and it clicks and you get how equivalence relations work and you get how products work, is very easy. It's one of those, and there are lots of those throughout all of mathematics. And something that might help with this type of construction is the second step, which is going from the integers to the rationals. And the reason it might help is because we're going to do essentially the exact same operation. Now, what we were doing with the natural numbers before is that we don't have a way, we're kind of like adding subtraction in. That we can add things like 1 plus 2 equals 3, but there's no way to do like 1 minus 3 because there's sort of missing elements there. And so what we do is we add those elements in by taking these products, and then we mod out by this relation such that things make sense. We don't get too many elements, and we don't get ambiguity with our operations. Well, when going from the integers to the rationals, exact same thing. with our integers, now we have, now I'm not going to write the integers as like a comma b pairs. I'm going to use the better notation of -4 and, -3, instead of, writing all those pairs. Now we know that we can always do multiplication. -4 times -3 is positive 12, which you can actually check, I guess, with that construction from the page before. But now we want to see, well, can we always divide by 3? Because you can take 12 divided by -3 with the integers, but can you do -4 divided by -3? And so we'll do the same thing. We take our integers and we make pairs of them, pairs a comma b. And what does a comma b represent? Well, a comma b is really a divided by b. And we know that a comma b, we're going to mod out by some relations. You can't have b be 0, so we have a little bit of a limitation. A comma b is similar to c comma d. Well, again, we should be thinking a over b equals c over d. And when does that happen? Well, that happens if AD equals BC. And with this construction, I'll talk a little bit about it. Now, at this point, we have like -1, -2, -3, but we want stuff like fractions. And so how do we get, something like 1/4? What is this equal to? Well, this is equal to 1 comma 4. Add the little square brackets in case, which is also itself equal to 2 comma 8, using the relations above in this equivalence relation. And I can check that, division works, and I can show how addition and multiplication works with these things, and can show how ordering works. But I think I'm going to do the annoying thing that they often do in math lectures, where they leave this as an exercise. And the reason I'm leaving this as an exercise is because this is actually something that you've already done. That essentially, I wrote here a comma b equals a over b literally. I should really I'm going to write this more properly. But it's really that if I do, the equivalence class a comma b equals a over b literally, because this is just different notation. When you learn about fractions, you learn about them as pairs of integers. And you learn things that like, 4 over 6 is equal to 2 over 3. And all the while, this is just a different notation for this. And so you can do the exercise of, what is like a over b plus c over d, and it will be exactly the same as if I were to write this as, how do you do a comma b, this equivalence relation, plus, how do I define addition? Well, I'm going to need a common denominator, and I'm going to need to do all that stuff. But you can do that. Like, I know you can, because if you're watching this video, you've gone past, arithmetic in either elementary school or middle school or whenever they cover this. And so the funny thing is that this construction and the way to do addition, multiplication, and to show when things are bigger or smaller than other things is something that is done in middle school or whatever time in school they do this. And so I'll just leave that to you as another piece of practice of doing this mathematical construction of, starting with something, taking a product, and then modding out by an equivalence relation. And so this process of the Cartesian product modding equivalence relation, which happens a lot in mathematics and has already been used twice, and we'll do the Cartesian product one more time when constructing the complex numbers. I'm going to leave this as an exercise that if you want to practice with understanding how these constructions work. And the next thing to go over is the rationals to the reals, which this construction involves a lot more than what came before it. And so I actually think I'm going to stop it here and save this for another video. Maybe even two videos, because I'm doing both constructions. Well, you can do a lot of constructions for all of these, but I'm doing two constructions, the two most popular ones, Dedekind cuts and Cauchy completions. And I think I'll do one or two videos just on going from the rationals to the reals. But again, if there's any questions with any of this stuff, please comment and let me know, because I think it's important, and I want to get better at just explaining things or explaining math online.